Welcome back to Raylene Math. In this video we will look at sequences, defining what a sequence is, what the absolute value of a sequence is, what it means for an infinite sequence to converge or diverge, and how to connect sequences to functions of a continuous variable. So the first thing we need to know about a sequence is that it is nothing more than a list of terms, and we put them in order, the first term, the second term, the third term, etc. And we often write it in this notation, but we can really relate it back to something more familiar, a table of values for x and y, where x is a continuous variable taken from the real number set, and y is the output of some function, in this case the reciprocal function. We can call that an f of x, where f is the 1 over operation. X can be any real variable except because of the domain restriction, x can't be 0. And so x could be a negative number, x could be a decimal, x could be a fraction, it could be a whole number, or an irrational like the square root of 2 or e or pi. And so we can plug these values in and get the corresponding y value. Similarly, the output value of a sequence, just like y is the output of a function, the output value of a sequence is an. And so the output is going to be the reciprocal of the n values, where n is contained in the integers, or if we restrict to the positive integers, we get the counting numbers, the natural numbers. So the set of n values are the set of numbers 1, 2, 3, etc. And unless otherwise specified, when we don't have any bounds here for a sequence, it's assumed to be that n starts at 1 and increases by 1 to infinity. So we normally write a sequence without indicating what the input values are because they are quite familiar, the counting numbers, 1, 2, 3, 4, 5. And as a result, we don't need to indicate the inputs as well as the outputs. We often just write the outputs in the form of 1 over 1, 1 over 2, 1 over 3, 1 over 4, etc., separated by commas. The dot 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 here indicates that the sequence goes on to infinity. But we could write our sequence as an input-output table of pairs or ordered pairs like this by indicating the n values 1, 2, 3, 4, and therefore 1, 1/2, 1/3, 1/4, etc. It's really nice to be able to look at a sequence from a graphical point of view, and Desmos does a very good job of allowing us to do this. We can make a table by clicking on the Add item and go to Table, and then we have to use a variable name here and the expression over here without an equal sign. Now I can change this to n and change the corresponding variable here to n. And as a result, we can see that there's a link between the reciprocal function and the sequence 1 over n. We can see that if x is an integer, the sequence outputs and the function outputs are at the same heights. Now in this particular graph, we see that this function has a horizontal asymptote at y equal to 0. And that's going to be important in just a minute. But this is a really useful tool for helping you to visualize sequences and to connect it to the continuous function. So let's go back. The next thing we want to look at then is the definition of the absolute value of a sequence. Here we have a sequence given by alternating terms, and if we want the absolute value of the sequence, we simply take the absolute value of each individual term, which gives us a sequence of constant values 1, 1, 1, 1, etc. And this could be simply written as the sequence of the constant function 1. If we were thinking of a graph, we would have a graph of the function y equals 1, and then the input values for the sequence would only be 1, 2, 3, 4, 5, etc. And so we would just plot points that are disconnected or discrete to graph the sequence of the absolute value of an. So now if we're interested in finding out what it means for an infinite sequence to converge or diverge, we really can see from the graph what's happening. We talk about a defined value or a limit value existing, meaning that the value is a single real finite value. In order for an infinite sequence to converge then, we want it to converge to one single real finite end behavior value. So we are really looking at calculating an end behavior limit on the right end as n approaches infinity of the nth term, the function f of n of the sequence. Graphically speaking, this means that we have a right end behavior. We're talking about the right end behavior of the sequence. And graphically speaking, again, we're looking for a horizontal asymptote. So we're zooming out on the graph and seeing if the y-coordinates approach one single real defined finite value. So we say that the sequence of an terms converges if the end behavior limit exists. In other words, if the function f has a horizontal asymptote on the right end, because we're specifically focusing on positive integers, so n is going to approach positive infinity. Similarly, the sequence diverges if the function does not have a horizontal asymptote, which means that the end behavior limit on the right side does not exist. And does not exist means to be undefined, means to be not a single or not a real or not a finite value. So we can look at a couple of different examples. Here we have some different functions, and the functions are given as the output for the an. Make a table of values for each function, make a graph of the function and of the sequence, and then justify using some algebra working out of a limit to see if the sequence of an terms, specifically if this sequence, an, for the nth term expression as given, to see if that sequence converges. So I'm going to take a look at the first one and do it with you and leave you to work out the rest of them on your own, using your own knowledge, using Desmos and technology as a confirmation of your understanding. So the first time through, we're going to substitute n equals 1 through 5 into the expression, and we're going to get 3 over 2, then we're going to get 4 over 3, and then 5 over 4, 6 over 5, and 7 over 6. And what we really want to know is, as n approaches infinity, does this limit, this output height value, exist or not? And if so, what does it equal? What does the n approaching infinity limit value equal? Well, in the case of looking at y equals x plus 2 over x plus 1, we can write this as a proper fraction by seeing this is x plus 1 over x plus 1, which is going to be dividing into this, gives us the proper fraction form of 1 plus 1 over x plus 1. If we want to take the limit of this function, I'll write it above here, and we'll take the limit as x approaches infinity to both sides of y and the proper fraction form. We can see that the limit value, or the height that y approaches as x approaches infinity, is equal to 1 plus 0, which is 1. And therefore this function does indeed have a horizontal asymptote at y equal to 1. And as a result, the first sequence of an will converge. Let's use Desmos to explore the graph of both the function and the sequence, as well as the table of values to confirm numerically and graphically that this sequence actually does converge. So we have the sequence here, n plus 2 over n plus 1, and the function x plus 2 over x plus 1. If we zoom out, we see a horizontal asymptote. And if we make more values here, big values for the n, we can start to see the output an values getting closer and closer and closer to 1. In fact, if we use very, very big value for n, almost approaching infinity, we see that the calculator starts to call this 1. So indeed, we do have a horizontal asymptote from numerical, graphical, and algebraic approaches by using some algebra techniques for calculating the limit, as we saw here. So I want you to use the same kind of thing to look at the other examples, B, C, D, and E. Look numerically, graphically, and algebraically to evaluate the limit as n approaches infinity and decide whether the sequence converges or diverges. I'm going to pause the video and give you a chance to try all of these. Ideally, you should be able to do most of these graphs or algebra by hand and then use the technology to confirm. Okay, so try it and check back in a few moments. Okay, so here are the results for the 4 different sequences. We have the first part B converges, part C converges, part D diverges, and part E converges. Now, methods here have been purely algebraic, but to make sure you really understand the connection between the sequences and the functions, draw the graph, look at the table of values, and make sure from a multiple representation point of view, graphically, numerically, and algebraically, that you understand the convergence of sequences. Okay, in number 8, there are a few more examples. We have another famous and important sequence called the alternating harmonic sequence, which is just the same as the harmonic sequence, but with alternating values. So we can take a quick look at Desmos and make an expression here of -1 to the n. all over n. And we cannot come up with an associated function with this because -1 raised to a continuous variable is going to be a problem because we're going to eventually have -1 to the 1/2, which would introduce imaginary or complex numbers. And so we won't bother coming up with an associated continuous function because it's not possible for the kind of base that we have for the exponent being negative. So we'll just delete that and we'll look only from the sequence, but imagining the graph is jumping around. It's quite discontinuous really if we're trying to connect it. We do see though that the vertical distance from the AN value, A1, A2, A3, A4, sometimes the outputs are positive and sometimes negative, but the magnitude of them, the absolute value of them, represents the vertical distance to the x-axis. And that vertical distance, the magnitude of the AN, is decreasing. And as a result, this limit is going to exist. And that limit will equal to 0. So the alternating harmonic sequence will converge. So take a look at the rest of these. I'll pause the video and then you can check your answers in just a moment. Here are the results for each sequence. Both the harmonic and alternating harmonic sequences have a horizontal asymptote, if you will, or an existing end behavior limit, and so both sequences converge. The arithmetic sequences both diverge. We see when we plot these, let's take a look at the second one. It's a bit easier for me to remember the numbers. If we go to Desmos and we want to plot the 5 minus 3/4 n sequence, that this is a sequence of points that lie on a line. And so it's related to the linear function y equals 5 minus 3/4 x, where the 5 is the y-intercept and the slope is the -3/4. So because a linear function is one-to-one, it never turns around, it only ever increases or decreases, we are not going to get a horizontal asymptote, and therefore the limit of the sequence nth term will not exist. And so that sequence diverges. The same thing is true for the first one. We have a slope of √2 and we have a y-intercept of -pi. The slope is positive, and so the first sequence is an increasing linear sequence. Y approaches infinity as n or an approaches infinity as the input n approaches infinity. Looking then at the next two sequences, geometric sequences have a constant in the base and a variable in the exponent, which reminds us of exponential functions. Furthermore, this first expression has a base that is more than 1, so it represents exponential growth, and the next one has a base of 1/2, which is between 0 and 1, so we have exponential decay. Thinking about those graphs, exponential growth means that the output increases to infinity, so this sequence diverges. The next one converges because the horizontal asymptote of an exponential decay function is y equal to 0. And the last case, we have a divergent sequence because we have two heights. If we take a look at the graph, we can simply write the expression as -1 to the exponent n and turn off the linear function. We see that the heights approach two different heights, and a failure for the limit to be a single height means that the value is not defined. And so the limit does not exist because an is approaching +1 or -1. So hopefully you have a pretty good understanding about sequences now, especially in connection with the continuous functions or functions of a continuous variable x. That's all for now. Stay tuned for more on sequences. Thanks for joining Raylene Math.